Hello again. We're going to discuss today phase equilibrium and how we can construct phase diagrams. As we've discussed in the previous lecture, phase diagrams represent regions in temperature and composition, usually at constant pressure, and the regions have different phases. And a phase is a region in space that has a different and unique structure. And the structure could be liquid, for example, or the atoms could be arranged in a particular way, like a phase center cubic solid, or a body center cubic solid, and so on. So the idea here for this part of the course is to be able to understand phase diagrams and be able to compute the regions where the phases are in equilibrium if we know the basic thermodynamic data. So I'm going to start the lecture here, and here's the title of the lecture, in which we have material processing and the study of phase diagrams. So first, I'm going to discuss the concept of chemical potential for two species and one single phase. So we will talk today in this part here about having basically two elements, A and B, and the two elements are mixed together in a unique phase. Say this phase will be a liquid, or they could be a solid. And the equilibrium is going to be defined between phases, is going to be defined in terms of the chemical potential. We need to first be able to write down what the chemical potential is from the Gibbs energy or the thermodynamic data that we have. So let's assume now that we have a graph that represents the variation of the Gibbs energy with the concentration of one of the species, say the concentration of species B, and then we will write the chemical potential and see how it looks like on this graph. So let's do that. So in here I have a particular graph, and the graph is going to be for the on this side here, this will be the Gibbs energy, and on this side will be the concentration of B. So we're going to limit B from 0 to 1. So in this case I have this axis here would be x sub B, and 0 to 1 as a concentration. This is molar concentration, very important. Then the graph is going to be the value of G as this function. So if we plot G, then it will start at a specific value for element A on this side because we don't have B, and it will end up with another value for element B when it's in its pure state. And in between is going to vary, and let's take the variation to look like this. And let's also, to elucidate the concept, we're going to assume that we have a particular composition here, and this particular composition is indicated at this point. And then we take, let's say, a tangent to the graph. So it's going to change the color to have the tangent to the graph that intersects both sides. And then what we will do is we'll just indicate here that this is x sub B and super 0. This is a particular concentration, and we will show that the intercept on this side is the value of mu sub b in the phase, on the single phase, and the value on this side is mu sub a. So let's continue understanding. We want to write equations now for that. So what we want to do is actually look at what is the definition of the chemical potential as the rate of change of the total Gibbs energy with respect to the concentration, and from that we will show that the intercepts on both sides represent basically the chemical potential of element A and the chemical potential of element B at a given concentration. So if we want to do that, we will basically continue here to show that if we just clear this page, then we know that the chemical potential is for element B, we derived this equation before, is equal to G, the total Gibbs energy for the system, plus X sub A times the derivative of G with respect to X sub B, and this derivative is evaluated at the particular concentration X sub B super 0. And this, similarly, we can write mu sub A as equal to G plus X sub B times dG by dx sub A at X sub B 0. So these are two equations. Note that in the top equation we have the B here, and then it is we have X sub A on this side, and we have dG by dx sub B at X sub B 0. And note here that we have X sub A, mu sub A is written in terms of X sub B and dx sub A. So that's a little bit cumbersome because we want to write the equations all in terms of X sub B. So we don't want X sub A and we don't want X sub A here. So what we'll do is we will actually remove this and rewrite the two equations immediately. So if we do that, then we're going to use the fact that X sub A is equal to 1 minus X sub B, and d by dx sub A, we change it to minus d by dx sub B. So this way we have basically the previous two equations can now be redone, and we will get the following form. So if we just do the previous two equations, we get mu sub B now is equal to G plus 1 minus X sub B times dG by dx sub B at X sub B 0, and mu A is equal to G minus X sub B times dG by dx sub B at X sub B 0. So what do we note here? We note that we have the value of G, and then we have a little bit extra. A little bit extra is the slope times the run. The run is meaning this distance here. I'll show you on the graph. And again, we have here mu sub A is equal to G, and then you have the slope here times the run, which gives you in terms of X sub B. So if we look back at the meaning of those on the previous slide that we have, we will see that the interpretation is the following. So if we have now, let's replot one part of the Gibbs free energy, let's say on here, and then do the replotting, and we will assume that we have the g function is like this, and now I took a common tangent, and now if you look at this height here, this from here to here is the g, and this height here from here to here is the slope times the distance d. So this distance here from here to here, the slope is dg by dxb at xb0, and the distance is basically 1 minus xb, because from here to here is x sub b. And therefore we have shown now that we can obtain basically the chemical potentials once we have a model for the Gibbs energy as a function of the concentration. So the key is that we need the Gibbs energy as a function of the concentration of the species. Note that the Gibbs free energy is a function of temperature, function of the pressure, and now it will be a function of the concentrations themselves. And that functional dependence comes from the mixing, which we will have now to deal with, so that we can find a model for the Gibbs free energy of a mixed two species system. So what we'll do in the rest of the lecture is that we will go to a two species system, single phase, and we will have to derive some model for the Gibbs free energy as a function of the concentrations, and then from that model we can take the derivative and find the chemical potential and study its equilibrium. So let's go to the next phase here and look into that. So suppose now that I have two systems, and what I want to do is basically I want to find the Gibbs free energy. So I would like to get the Gibbs free energy for the two systems as x sub a times the Gibbs free energy of A plus x sub b times the Gibbs free energy of element B plus delta G mix. So that's kind of where we are right now. We want to find delta G mix. And delta G mix is going to be equal to delta H mix minus T delta S mix. And in the ideal case, then the delta H mix, we found it to be 0. And we found that the delta S mix is R times the sum of xi ln of xi, which means xa ln of xa plus xb ln of xb. So if you look at this picture that we have here, then basically what we're trying to do is go away from this ideal situation, because the ideal situation, we have only the contribution of the entropy to the mixing in the Gibbs free energy, and that can give us a curvature in the curve. If we look at the relationship between G and the concentration, it will get some deviation from linearity. However, we would like to go a little bit further, and we want to look at an atomistic model that can give us the enthalpy of mixing. And that's what we will do now, is look at an atomistic model to give us an idea about the enthalpy of mixing. So let's try to do that here. And in here, I'm going to start by saying that I have two boxes that I would like to mix. So I have basically one box here, And I have also another box that may contain different amount of material. And inside these boxes I have one type of material, and inside the other box I have another type of material. So I have material like this. So I have atoms of different material. And I am mixing these two together. So if I look at the total system, and the total system here is going to be expressed as the sum of two pieces. And if I have n moles, so I have n moles for the total system, and I have initially the concentration, fractional concentration of A species, and this is B. So X sub A and X sub B are given. So I also know that I have bonds between these atoms. So I have, if you have an atom like this one, for example, then it's bonded to all of the neighbors. So you have some neighboring bonds. So the neighboring bonds, we're going to assume that we have Z coordination number. So every structure of matter, the atom is surrounded by a certain number of elements or atoms, and we know the coordination number. For example, in FCC, the coordination number is 12. So here, if we're counting the number of bonds in the B side, for example, the number of bonds, what we counted for the B side, is the total number of atoms, which is X sub B times N, that's the total number of atoms, times the coordination number. Each atom has a coordination number. And however, I'm double counting the bonds, because if I count it for this atom, I'm also counting this atom. This atom will have the same bond. So this bond from here to here is the same bond from here to here. And therefore, I'm double counting. And therefore, the number of unique bonds is equal to this quantity here, X sub B times N times Z over 2. And if I want to compute the energy or the enthalpy of the system on the left side, let's say that if we have the energy per bond is EBB. So I'm going to write this. This is the energy per bond. Then I have now the total enthalpy for the left-hand side is X sub B N Z over 2 times E sub BB. So that's the total energy for the left-hand side. So let me continue here and move on to what we're going to do. So what we will do is the following. What I'd like to do is now calculate the energy of the system in its two pieces, the A and the B piece. So the B piece we figured is X sub B times N, that's the total number of atoms, times Z, coordination number, divide by 2 because you're double counting, multiply by EBB because that's the energy per bond. So that is what we have for the left side. We're going to add the right side similarly, and that will be the total energy content or the enthalpy of the system when it's unmixed. Now we're going to mix them together. When we mix them together, then we will have NAA bonds, and then we have NBB bonds, and then we have NAB bond. So we have like 3 types of bonds. 2 types similar to before, and 1 type that would be a little bit different because the surrounding can be different. So what you have to remember, because I'm going to write it down, is that in the mixed state, I'm going to look for the fraction of atoms that are alike. So I'm looking for the BB bonds. Then I'm going to find first the total number of atoms of B, and then multiply that by the fraction of B atoms that are surrounding me. So there's going to be another fraction that comes in, and that can give me the total number of BB bonds. And I'll do that similarly for AA and then for AB. Notice that for BB and AA, we double counting. But for AB, we're not double counting because it's a unique bond between A and B in that case. So let's write now the full expression for the enthalpy after mixing and the enthalpy before mixing, and take the difference, and that will be the delta H mixing in the following. So if we continue this, then we would have now the delta H mixing is given by the number of AA bonds in the mixed state times EAA. This is the energy per bond, plus the number of the BB bonds times the energy per bond between the BB, and the number of AB bonds times the energy between the A and the B type atoms, minus the unmixed state, which is, we figured, NZ over 2 times X sub B times EBB, plus X sub A times EAA, because we don't have AB type bonds. So, for example, the NAA is going to be, I have N atoms and I have X sub A, so this is the number of A atoms in the mix. And each A atom, I'm looking for the guys that are similar to me in the surrounding, and their fraction is X sub A. So it comes out to be like this. And I have a coordination number. Each atom has a coordination number Z, and I'm double counting, so I divide by 2. So if I convert this, I will have NZ over 2 times XA squared. And since we want to write everything in terms of XB, then we're going to write it like this: 1 minus XB all squared. So that is the AA, NAA, and therefore I can substitute it up there. So if you just look at now the equation that will arise, you will have the mixed state, you will have quadratic terms like 1 minus X sub B squared, or X sub B squared when we come to the BB bonds, or X sub A times X sub B when we come to the mixture. And then in the unmixed state, it's all linear terms in the concentrations, because the number of bonds is proportional to the concentration. And we will have now delta H mixing. I'm going to go a little bit over that fast so we can finalize the equation. So if we do that, then the next line, we will write now the delta H mixing is equal to NZ over 2. It will be common to everything. And then I will have 1 minus X sub B squared times EAA. That's in the mixed state. In the unmixed state, I have NZ over 2 times 1 minus XB. So 1 minus X sub B times EAA. So that's the difference in the AA. And then I go into the BB. So it'd be NZ over 2 times X sub B squared EBB minus NZ over 2 times X sub B times EBB. And now we just figured out the game. So that continue on now. The only term left that is in the mixed state that doesn't have a corresponding one in the pure state is the AB bond. So BB times XA, and XA is 1 minus XB, EAB. And when we collect terms, I take NZ over 2 as a common factor, and I will have 1 minus X sub B, E times AA, EAA, plus, well, it will be, I'll take that back. So it'll be minus X sub B times, well, I think I have to retract this. So it will be 1 minus X sub B times EB or EAA times 1 minus X sub B minus 1. I was trying to do it slowly. So we get this, and then plus another term, which is X sub B times EBB times X sub B minus 1, plus the term that is cross term, which is X sub B times 1 minus X sub B times EAB. So that will be the total enthalpy of mixing. So I can continue this now and modify it maybe and make it simpler. And I can make it simpler by writing now that finally I have delta H mixing is equal to NZ over 2 times X sub B times 1 minus X sub B times a factor omega, where omega, well, let me retract this for a second and write it in explicitly, times here, and then I have a factor, and this factor is twice the energy of bond between A and B minus EBB minus EAA. And that we can write it in a little bit better form if we consider the following. So if I write it like omega, so I'm going to let omega be equal to this 2EAB minus the sum of the BB plus the EA times the NZ over 2. I can call this the interaction parameter because it describes the interaction between the A and the B when they are mixed together. So in this case, I can write the delta H mixing. So I can write delta H mixing as simply equal to omega times XA times XB, because XA is 1 minus XB. And therefore, the mixing enthalpy came out to be pretty cool, and it all depends on the value of this interaction parameter. So if you look at it, you'll see here in this equation I have this omega, and then this is the product of the concentrations. So whenever we do the mixing between elements, then we get the mixing enthalpy is proportional to the product between the concentrations times an energy factor. And the energy factor here is the difference between the energy of the unlike bonds and the average of the energy AA and BB. So that difference here determines the sine of omega, and that's what we're going to consider. That's very important, the sine of omega and how it influences the shape of the free energy as a function of concentration. So let's just continue this to show that the sign is very important, and we will do that by writing now that if we let x be xb, for example, then xa is equal to 1 minus x, and things gonna look simpler as a function of x, then g as a function of x, and we have this in the back of our minds as really xb, but it makes it easier to write a function of x from these parameters. Then we have omega times x times 1 minus x, and then I have RT, and RT times ln, let me just write here, times x, ln of x, plus 1 minus x times ln of 1 minus x. So 1 minus x. And this type of model here is a simple model that can tell us the dependence of the Gibbs energy on the concentration of one of the two species. So in this model we have these two terms here represent the mixing, straight mixing of the Gibbs energy of the two components. And then this amount here represents delta H mixing, and this amount here represents T delta S mixing. And therefore, if we represent this function, it will have actually to be represented as three different functions. So this is F1 in here, and this is F2, and F2 will depend on the sine of omega, and then we have also here F3 that is negative, because we know that the logarithm of all of these exponentials is negative. So from now on, we will have to consider cases that relate to the sine of omega in this F2. So let's consider now here we have two species and a single phase, and the two species in a single phase here. I have here, this is your delta H mixing. In the case of I'm going to emphasize that this is called the miscible solution. So miscible solution is a solution that is stable. It doesn't separate into phases. You mix two elements. They're always together homogeneously in space. And in this case, delta H mixing, so let me write it here, case 1. In this case here, I have the delta H mixing is less than 0, it's negative, and the omega parameter in this case is also less than 0, so less than 0, and it means that mathematically speaking, I have the bond energy between A and B is less than 1/2 of the average energy between AA and BB. So when they are together, they like each other, so the energy decreases when they see each other. So in this case, it's like attractive, and they like to be together, obviously, so they don't want to separate from one another. The energy per bond decreases when they come together. So in this case, I will have, if I just point out, this is a delta H mixing, negative, and T delta S is always negative, so you have a decrease here, and the total delta G is the sum of these two, and then you have to add on top of this the original curve between this point and this point is the linear mix. So this is G sub A on this side and G sub B on this side. So this is what I pointed out. This here is F1, this here is F2, and this is F3. So if we look at our F1 is right here. So you have F1 is the linear straight line between GA and GB, and F2 is like a parabola, but it has a negative amplitude here that makes it go negative, and then the F3 is basically the entropy term, and the entropy term is have natural logs, so it gives it that kind of curvature that we've seen. So these are the three pieces that we talked about here that give us the delta G, which means that this case is what we would term is fully miscible. So it's a miscible system. For example, if you have sugar, and this side here sugar, and this is here water, and then you mix them together, then the sugar is totally miscible. You're going to have one solution of the two species, and they are just completely mixed together in space. So now let's look at the next stage, which is I have two species, but I have a single phase, and this single phase that you'll see here is going to turn into two phases, and it will create what is called the miscibility gap. And this is similar to say the idea of increasing the amount of sugar in the water, and at let's say you're reducing the temperature as well. If you're at low temperature, then the sugar there's a certain concentration of sugar. If you increase it, it will start to crystallize into a solid in the bottom. So you'll have part of the liquid that has sugar, and then the other part will have solid sugar. It has some water molecules. So you separate into two phases. One phase that is rich in water, and another phase that is rich in sugar. And that condition exists when we have delta H mixing switch sign, and that happens as a function of temperature. So if the delta H mixing for a given temperature becomes positive instead of negative, then they repel each other. They don't like each other, and that can create this miscibility gap that I'm going to talk about. So here, this condition is that I have here to start with, I have three systems. I have basically the omega factor that I'm talking about here is less than 0. This is a result, sorry, it's greater than 0. This is a result of the fact that the AB bond is greater than 1/2 of the sum of the AA plus the BB bonds, and in this case delta H mixing is indeed greater than 0. So it goes up. So this is the delta H mixing becomes positive. And here, if we have now a different color, maybe to connect these 2 points here, then we basically have this is our F1, and this is our F2 now, and this is our F3 now, and the sum of F1 plus F2 plus F3 gives us the delta G, and the delta G that we have is going to be, let's say, in this curve that actually is the sum of the three curves that we've seen before. So this is the delta G that is the sum. And note here something very interesting in delta G is that in here the curvature of delta G has changed. the curvature in this region is positive. Whenever it's concave upward, is positive curvature, and whenever it's concave downward, then it's a negative curvature. So it's a negative curvature, this is a positive curvature, and this is a negative curvature. What is curvature? So curvature is basically curvature is the second derivative d2g with respect to xb squared. So we're going to call this g double prime. So g double prime here is positive, and here is negative, and here is positive. And what happens here is that if you take a concentration at x sub b bar, then its Gibbs energy is right at this point here. And this point here is too high. It can actually split, and it can split into concentration here, xb double prime, and a concentration at the other minimum, xb prime. Now, if you compute the linear combination of the Gibbs energy at xb prime and the Gibbs energy at xb double prime, it will come out to be about here. Any linear combination of these two will be, well, it will be like somewhere in between, like you just connect a straight line between the two. You can show that a linear combination of these two will be at this point. This point, the Gibbs free energy is lower than the Gibbs free energy of the original mix that we had. And therefore, this original mix has too high of a Gibbs energy. It has a driving force to reduce its Gibbs free energy. So what's going to happen is that it will go from here, and it will come to a point where it indeed is split into two regimes. One has this concentration, xb double prime, and one has this concentration, xb prime. This will constitute a new phase that is rich in water, and this will constitute a new phase that is rich in sugar. So the sugar will be very high concentration in this region and low concentration in here, and vice versa. And that is the idea of phase separation and the miscibility gap that we are talking about. Note that the curvature is kind of an important aspect of this problem. And I talked about the curvature. So the curvature, if you go up here, the curvature is maximum. Okay, the first derivative is minimum, is 0 at this point. The curvature is maximum, and it's negative. The curvature at the inflection point is 0. So if I look at the inflection point and I want to have the curvature here, it will be 0. And then it will switch to a positive curvature here, maximum. So if you take the first derivative at this point, you'll find it 0. At this point, the second derivative is 0, and therefore, without going into more elaborate details, there's going to be a region between the highest curvature and the 0 curvature where you have instability. So this is an instability that will happen and will grow up to the point where the curvature is 0. And the instability is going to drive the system spatially in space to separate into two phases. And beyond this point, which is the inflection point, all the way to the minimum, then you have any small fluctuation will kind of separate the two systems, but it will be still some sugar in the water and some water in the sugar, but they're not very strongly separated. So if I look between the two inflection points, it would be a regime that we're going to call spinodal regime, and the spinodal is total separation in space, high sugar content, sugar crystals, and then you get water with a little bit of sugar. So you have like kind of the striped concentrations, and between the inflection point and the minimum in the Gibbs free energy, you have a regime that has like fluctuations will grow and will separate at a smaller scale. So to show that, I'm going to now move on to the next stage and discuss it in terms of the structure of the equation. So the structure equation, this is delta H mixing minus T delta S. This is your delta H mixing. You wrote it here with a new parameter beta, but it's essentially the same as our omega. So let me change it to omega. So this is your omega. And x sub a, you can write it as x. X sub b, you can write it as 1 minus x. And therefore, what I want you to do is look at now the previous graph. And the previous graph, I have two important points here. I have the first derivative at this point is 0, and this is an important temperature, and the temperature that corresponds to that point, this is an important value for G. The temperature at that point, at that value of G, is the temperature that can cause the immiscibility. So this will be an important point to find, and we can find it by taking the first derivative and equate it to 0. And then these two inflection points, we can find them if we take the second derivative and equate that to 0 as well. So what we'll have is we take this and plug it in to our previous equation, like let me just write it down. So this is the full equation that you have here, and this full equation, you can take first derivative and second derivative, equate them to 0 to get these important points on the curve. And then what I want you to do is actually show the following as an exercise. So we want to show that if you, in the miscibility gap, you can determine that by the boundaries are obtained by calculating the first and second derivatives of the phi energy respectively and setting them equal to 0. So we have this temperature T sub C that we can find from the solution, and you find that the solution gives you the following. It can give you now the value of, in this case, I have the T sub C value. This is the temperature, critical temperature at which you have immiscibility. And we can prove that the product of the concentrations, or it separates, is given by that. And that this is, again, the ratio. So we have the region for the spinodal and the region for the immiscibility or the phase boundary are given by that. So if we look at this, now I'm going to show it to you graphically here. So if we look on this graph, then you see that I have, this is the total G at the temperature T1. If I reduce the temperature, then the value of G will have an inflection because the delta H mixing at that temperature switch sign. And if I go to T3, this will be also exaggerated here. The corresponding phase diagram that you have is shown in the bottom, where at T1, here I have at T1, if at any concentration that I choose at T1, I will have the corresponding Gibbs energy is the red curve, which doesn't have inflection, so it is totally stable, and therefore there will be no immiscibility. If I go to T2, then as we mentioned here, between the two minima, you will have phase boundary. So this is a phase boundary. And then between these two inflection points, you will have what's called the spinodal boundary. So the phase boundary, you can construct it from the two points at the minima, and therefore you get, this is the phase boundary here, and that will be that will give us what's called the phase boundary. If you're at any temperature T3 and the concentrations inside here will have essentially two phases. So they will actually separate into two phases, one rich in sugar, one rich in water, as we mentioned before. If we consider the spinodal boundary, then the situation is going to be a little bit different, and then we have this graph. So in this graph, I have a, it is essentially the graph of the previous equation that is totally symmetric. If you look at the previous equation that we discussed before, and we bring it here so we can see what it is. This is the equation that we discussed, and if you look at the equation, then it's totally symmetric because this term is symmetric with this term. This term is symmetric in both x and 1 minus x, and this term is also symmetric. So all of these are symmetric, which tells you that if you plot it as a function of x, it has to have some kind of a minimum or a maximum at x equals 0, x equals 0.5. So that's what we're going to have here when we discuss the graphical plotting of this condition. So in this condition that we discussed for the previous equation, I have now a graph that, on this graph for the Gibbs energy is like so. So it's kind of exaggerated a little bit here, and the curvature is a negative here and positive here, and then I have two significant points on this side, the A and B, and on this side I have the C and D, and the point A, if you vary now the temperature, so if you do the same curve at different temperatures, for example another temperature, you would have another curve that looks like this. So this will be at T1 and this will be at T2, and then you again find the inflection points and the minima on at any given temperature. Then you plot the temperature versus the molar fraction, and you identify the locus of all of the minima. The locus of all of the minima will give us the phase boundary, and the phase boundary would be curve number 1. And if I identify the locus of all of the inflection points, that's going to give me the spinodal boundary, which is right here. So this is spinodal, and this is like fluctuations can also separate, but not very strong separation between the different phases. And here we have a single phase, so a single phase in this regime. And with that, I think we have a reasonable understanding of the concept spinodal. There are more to it than that. We would have fluctuations that can grow like waves, and then we can develop an equation for the pattern that will take place as a result of these fluctuations. So we'll leave that from discussion at this point and move on to show what it is to have this spinodal decomposition. How does it look like? So on the right hand side here, I have one region in space and another region in space that are kind of close by, and the concentration of the species are the same in the two regions. So if you look at the density of one of them, rho 0, is the same here as the same here. But now suppose that you're getting closer to the phase boundary that I talked about. If I'm close to the phase boundary, I have a fluctuation in the concentrations. So you have low concentration here, high concentration. You get one region in space that has lower concentration, another region that has higher concentration. Normally, if we're in normal situation, then we would have a fixed diffusion which will push the higher concentration back into the lower concentration and make it more uniform. But because the delta H mixing make them like each other, then whenever this guy goes to the other side, it feels more comfortable here and it wants to stay. So it leads to what we call a phenomenon that is called uphill diffusion. In other words, diffusion not down the concentration gradient, but the diffusion is up the concentration gradient, as you can see here. So with that, if you look now at stronger fluctuations, these are small fluctuations. If you look at stronger fluctuations, then the diffusion is going to sharpen any boundary, and you can separate. This is the sugar crystals, and this is the water that has a little bit more sugar crystals, and so on until you have crystallization and regions that have nothing in between. And that is essentially the spinodal decomposition concept. This is to be contrasted with nucleation of a new phase, which is like a precipitation reaction. So in a nucleation, what have is that we have the two regions in space here, the same concentration, and then you have a fluctuation. This guy lost a little bit to this guy. Then nature is going to push that back in here because it's the same, the new batch of the new tribe that went from here to here felt about the same, so it goes back to here and you get uniform concentration. So this is for small fluctuations, unlike the small fluctuations here. For large fluctuations, then you get this guy here in this region. It can condense collectively into a precipitate, let's say. And the precipitate will accrete all of the species that are close by. And therefore, by normal diffusion, there will be a diffusion from this region to that region, and you get depletion here and growth here. And that is the idea of nucleation. From here to here is a nucleation, and from here to here is a growth of that species. So this is a fundamental difference between the nucleation and growth of a new phase versus a spinodal decomposition between two different phases. So we'll now have the understanding of the idea of spinodal. So let's now move on to discuss the phase diagrams and how we're going to compute the phase diagrams using the concept of chemical potential. So I'm going to start it now, and maybe we'll continue in the next the next lecture. So as we mentioned here, the chemical potential mu is for suppose that I have for equilibrium, we want to have mu of element A in phase alpha is equal to mu of element A in phase beta, and these two are computed at the respective concentrations. So this is important to point in here. So let me just write it down carefully. This is computed at the concentration, I'm going to call it XB in phase alpha, and this is computed at XB in phase beta. So at two different concentrations. That would be the equilibrium condition. The only way that this can happen is that if I have a common tangent, because this height from here to here is mu A in alpha phase, because it belongs to the alpha phase. This belongs to the alpha phase. And if I take the beta phase, which is green right now, and draw another tangent, then it will have an intercept, which is a green intercept here. And this green intercept is mu of A in the beta phase, evaluated at this concentration. So the XB in the beta phase is this concentration, and the mu A in the beta phase is the green height. So the solution is that the red arrow must be equal to the green arrow. This is the alpha phase is the red arrow, and this is the green on this slide. And that will essentially give us the equilibrium concentration. So to summarize this whole area is that we have learned that the equilibrium between species is governed by the chemical potential, and that in order for us to achieve equilibrium between two phases, let's say I have liquid and solid. These are the two phases, and I want to find the equilibrium between these two. What is the concentration of, let's say I'm making an alloy, and the alloy is iron and tungsten. So A is iron, B is tungsten, and then I have a liquid and a solid. So I must have a Gibbs free energy for the liquid phase, which is the mixture of these two, and I must have a Gibbs energy for the solid phase, which is a mixture of these two. If I take the common derivative of these two, the common slope, and I look at the intercept on the iron axis, or the intercept on the tungsten axis, that will give me the solution. In other words, that will be the common slope is going to give me the concentrations of iron and tungsten. That would give me the equilibrium between the liquid and the solid phase. So we're going to stop here, and then we'll continue in the next lecture on the idea of eutectic and the more practical phase diagrams.